Welcome to Lecture 3 of Module 8. It's entitled Particle in a Box. We're going to be solving for a particle in a finite square well potential, and we're also going to be deriving the Schrodinger equation in its familiar form from position space. So you're going to learn both about how to solve particle in a box and also about what the Schrodinger equation is and where it comes from, or at least one way that you can see where it comes from. So if you remember our general form for the ladder operator, the lowering operator took the form 1 over square root of 2m, momentum operator minus I h bar k superpotential, which we wrote as w of k prime x hat. We would then calculate a dagger a to determine the Hamiltonian. So a dagger a is equal to 1 over 2m p hat squared minus I h bar k commutator of momentum with the superpotential plus h bar squared k squared times the square of the superpotential. Now, in order for that to equal the Hamiltonian, we require the terms that are not p squared over 2m to equal the potential minus some constant shift, which ends up being the ground state energy. So v of x minus e must equal minus I h bar k over 2m commutator of p hat with w of k prime x hat plus h bar squared k squared over 2m times the square w squared of k prime x hat, the square of the superpotential. Now, if we recall, the commutation relation of momentum with a power of position was given by minus I h bar n x hat to the n minus 1. I believe we derived this in Module 5 or Module 6. We see that if the superpotential can be expanded in a power series, then the commutator of momentum with some function is going to act just like the derivative. So v of x minus e is going to be given by minus h bar squared kk prime over 2m, the k prime coming from the chain rule when I take the derivative, w prime of k prime x hat, plus the term that we had before, h bar squared k squared over 2m, w squared of k prime x hat. Now, if we define kw of k prime x hat to be minus psi prime of x hat over psi of x hat, at the moment it seems like I'm just pulling this out of my hat, and maybe I am, but you'll see there's an important reason why I did pull this out of my hat, because it leads to a great simplification. So we're going to write the superpotential times k by minus psi prime of x hat divided by psi of x hat. Then when I take the derivative of this, I'm going to get, when I take a derivative of the numerator, I'm going to get psi double prime of x minus psi double prime of x over psi of x. And then when the derivative hits the denominator, I'm going to get minus psi prime of x, or that'll become plus psi prime of x over psi squared of x times another psi prime of x from the chain rule. And so that just becomes a net of minus psi prime of x over psi of x quantity squared. So you see what happens is that minus sign out in front gets rid of the minus sign times the h bar squared over 2m. So I get h bar squared over 2m psi double prime of x divided by psi of x minus psi prime of x over psi of x quantity squared, and then plus the term that we had before, which is plus h bar squared over 2m psi prime of x over psi of x quantity squared. And here's where the miracle occurs. You see the terms, those nonlinear terms that go like psi prime of x over psi of x, they cancel. The squares cancel and they disappear because one is a plus sign, one is a minus sign, and I'm just left with the second derivative term. So there you have it. And now what we're going to do is we're going to multiply both sides by psi of x hat. So I get v of x hat psi of x hat minus e psi of x hat equals h bar squared over 2m psi double prime of x hat. I'm going to move the psi double prime of x hat term to the left-hand side. I'm going to move the e term to the right-hand side. And we get it in this form, minus h bar squared over 2m psi double prime of x hat plus v of x hat psi of x equals e psi of x. That's a second-order linear differential equation. And it has a special name. It's called the Schrodinger equation. But what exactly is psi? We need to answer that. And in order to answer that, it's suggestive that that psi is related to the wave functions we've been working with. And we're going to find that indeed that is the case. we have to start from the subsidiary condition for the ground state, which said that the A operator acting on psi is equal to 0. We can write that out as the momentum operator acting on psi is equal to IH bar K W of K prime X hat acting on psi. And then if we multiply both sides by a bra X, a position bra, you remember that the expectation value of X p psi is just minus IH bar d by dx of psi of X. And that W of K prime X hat, I can act that to the left and it'll become W of K prime X. So I'm going to get an IH bar K W of K prime X times psi of X. So we write that out. And now what I'm going to do is I'm going to divide both sides by psi of X. And you see what I have there is minus psi prime of X over psi of X. And it turns out to equal K W of K prime X. So this was the motivation for why I called K W of K prime X equal to minus psi prime of X over psi of X. So indeed, this psi of X, when it's thought of as a function of X, is indeed the ground state. So this Schrodinger equation is a linear second-order differential equation. And that's nice because there's lots of properties that are known about linear second-order differential equations. At the moment, it's only the linear second-order differential equation for the ground state wave function when E is equal to the ground state energy. We're going to see what the implications are of that or how we can generalize that in just a moment. The other thing I want to point out is at this stage, it's actually an operator equation that we have. So the way to make it into a regular differential equation would be to multiply it by a position x bra, position x prime ket, and put it as a sandwich, multiplying on the right and on the left. Then I'm going to get a coefficient that multiplies the bra ket xx prime. That's given by minus h bar squared over 2m psi double prime of x, now x a number, plus v of x a number times psi of x equals e psi of x, again, the x being a number. And that's going to be multiplying this bracket xx prime. And all that we do is we say that we require that coefficient to equal 0. If we require that coefficient to equal 0, then we get the Schrodinger equation. Okay, so that's the way that you can interpret this in terms of a Schrodinger equation. That's a regular differential equation on regular functions. All right, so the ground state is one of the solutions of this equation. It turns out it's the solution that has the lowest E eigenvalue. Now, it also turns out that there often are many more solutions with higher energy eigenvalues. They can be discrete solutions, as in bound states, or continuum solutions. And we can find all of them by solving this equation. When we find them, they are exactly the same solutions that we found from the factorization method. That's not completely obvious, but I'm telling you that that's indeed the case. So this means that the two techniques are completely equivalent to one another. And the factorization method is a representation-independent method that emphasizes the operator algebra, while the Schrodinger equation method is a coordinate space method because we're looking at the wave functions in position space, and it emphasizes differential equations and wave functions. Now, most quantum textbooks emphasize this differential equation approach. It solves for the wave function and the energy eigenvalues at exactly the same time, as opposed to the factorization method, which solve for the energies first, and then only later solve for the wave functions. Now, if you recall this isomorphism between the momentum operator and minus IH bar d by dx, derivative with respect to the position coordinate, then that leftmost term looks like the kinetic energy. It looks like a p squared over 2m acting on psi. That's because if I take the square of p squared, I'll get a minus I squared, which is minus 1. I'll get an h bar squared, and I'll get a second derivative with respect to x. So that's exactly what that first term is. Now we're now going to show how these two methods work for the particle in a finite square well. You're going to see that the two approaches do share a number of similarities, although they also have differences, and some of the aspects you'll find easier in one approach versus the other. I'm not going to try to quantify easy for you. Easy is really a rather personal thing, so what I think is easy, you might think is hard. What you think is easy, I might think is hard. So we're not going to have that debate that one method is definitely easier than the other. They're just different, but they both lead to the same answer. So if you prefer one versus the other, you can always go with one or the other. In this class, we've been emphasizing the operator approaches and the factorization method. So the problem we're going to look at is a finite square well, and the potential is depicted for you here on the right. We have to separate into three regions, 1, 2, 3. The leftmost region 1 and the rightmost region 3 both have a potential that's equal to 0, while the central region has a potential that's given by minus V0. Now, as you can see, this is a potential that is piecewise continuous. It has discontinuities at minus L over 2, and it has a discontinuity at L over 2. That's okay. We can handle potentials that have discontinuities. We're going to consider the bound states. Bound states are going to occur when the energy lies between 0 and minus V0. If the energy is bigger than 0, it's in the continuum, and there are no energy eigenstates that lie below minus V0. When we consider the energy of those eigenstates, which we're going to denote by E, we're going to write it in two different ways. In one case, we're going to write it as minus h bar squared kappa squared over 2m. And in the other case, we're going to write it as h bar squared k squared over 2m minus V0. Now, the first form tells you explicitly that this energy is negative. The second one tells you that it's bigger than V0. And of course, we must have that the h bar squared k squared over 2m term is not as big as V0 so that that number is negative. And indeed, that is going to be a requirement of our setting those two different equations equal to each other, as we've done here. Now, in regions 1 and 3, we have a differential equation where V is equal to 0. So this is easy to write down. We have minus h bar squared over 2m psi double prime of x is equal to minus h bar squared kappa squared over 2m psi of x. I simply took E and wrote it in terms of the first form. You also can see I can divide both sides by minus h bar squared over 2m. And if I do that, you see I'm going to get psi double prime is equal to kappa squared psi of x. That's a positive number times psi of x. I would like you to pause the video now and go ahead and figure out how to solve this. This is a second order linear differential equation with constant coefficients. We solve this all the time in Physics 155. So please pause the video and come up with the two general solutions to this equation. Okay, thank you for pausing the video. The two equations are just exponentials. A e to the kappa x plus b e to the minus kappa x, where a and b are arbitrary constants that I can't determine at this stage. You can see that because every time I take a derivative with respect to x, I'll get a kappa that gets pulled down. If I take two derivatives, I get a kappa squared. That works when I have a kappa and when I have a minus kappa. Note that e to the ikx does not work here because that would give me a negative number, not a positive number. Okay. Now, in region 2, we have an equation that's given by minus h bar squared over 2m psi double prime of x minus v0 psi of x equals h bar squared over 2m minus v0 psi of x. I've again written it now with the e being replaced by that second form. When I do it that way, you can see the minus v0 terms on both sides of the equations cancel. If I divide by minus h bar squared over 2m, you see I'm going to get psi double prime of x is equal to minus k squared psi of x. So now it's a negative number that multiplies psi of x with the second derivative. I'd like you again to pause the video and write down what the solution of this differential equation is. Okay, thank you for pausing. I'm now going to reveal for you what it is. It is sines and cosines, so it's c cosine kx plus d sine kx. And you can see if you take the second derivative of a sine or a cosine, you'll get a minus k squared times a sine or a cosine. And so this works perfectly, and those are the two solutions of the differential equation. So this is just summarizing the three facts that we've learned. We have in region 1, a e to the kappa x plus b e to the minus kappa x. In region 2, I have c cosine kx plus d sine kx. And in region 3, I have a prime e to the kappa x plus b prime e to the minus kappa x, because I don't know that those coefficients are the same in region 1 and region 3. And at the moment, I have 6 coefficients, and I've got to find a way to determine what they are. So in our first step, we're going to use the fact that this problem has symmetry. The potential is an even function. And when the potential is an even function, that means we can choose our wave functions to be even or odd. This comes from what is called a parity symmetry. I've not discussed this for you in the class very well, but you can think back to the harmonic oscillator solution, which also has an even potential. And there we saw that the wave functions did alternate even, odd, even, odd. The same thing is going to be true here. So we're going to restrict ourselves to even and odd functions. That reduces the number of terms we have to work out tremendously. So we're going to first work on the even solutions. So let's look in region 1. In region 1, the x-coordinate is negative, and it's going to go to negative infinity. Now, my psi of x has got to be bounded. Otherwise, I can't square it, integrate it, and have the probability be equal to 1. So that term b e to the minus kappa x is simply wrong. It can't be in there. So the b must be 0. So I have an a present. Now I'm looking at an even function. That immediately tells me I'd better pick d equals 0. And then to make it an even function, when I go to the opposite side, I can only have psi of x equals b prime e to the minus kappa x, because as x goes to plus infinity, that's the only term that decays. But for it to be an even function, I'd better make sure that that b prime is equal to the a. So what we find is in region 1, a is non-zero, b is equal to 0. In region 2, c is non-zero, d is equal to 0. And in region 3, b prime must equal a for it to be an even function. Okay, we have a matching condition as well. We insist that the wave function and its first derivative are continuous across the boundary. So let's look at that wave function. We're going to look at the boundary between region 1 and region 2, which occurs at x equals minus L over 2. I have to set psi of x in region 1 when I put x equals minus L over 2 equal to psi of x in region 2 when I set x equals minus L over 2. And that gives me a e to the minus k kappa L over 2 equals c cosine kl over 2. And then I have to do the same thing for the derivative. So in region 1, the derivative is going to give me a kappa a e to the minus kappa L over 2. And the derivative of a cosine is minus a sine, but I'm evaluating that sine at minus L over 2, so it's going to, the minus sign will cancel. I get a plus sign, so I get kc sine kl over 2. Well, that's good. We now have 2 equations, and we have 2 coefficients we're trying to solve. But it turns out these are homogeneous equations, so it's not that easy to directly solve them. And indeed, what we're going to do is we're going to take the ratio of psi prime of x over psi of x. And when I do that, starting from the psi prime of x, I have kappa a e to the minus kappa L over 2. If I divide that by a e to the minus kappa L over 2, I'm going to just be left with kappa on the left-hand side. And if I take kc sine kl over 2 and divide it by c cosine kl over 2, you see I'm going to be left with a k tangent of kl over 2. So that is our consistency equation that guarantees that the derivative and the wave function are continuous across the boundary. All right, let's now do the odd solutions. So in region 1, again, a is non-zero, b is equal to 0. In region 2, I'd better pick d instead of c because it's an odd function. And again, a prime has to equal 0, b prime is non-zero, but I'd better pick b prime equals minus a because it's an odd function. All right, our matching conditions are the same. The wave function and its first derivative must be continuous. Again, I look at the boundary region between region 1 and 2, and we're going to find that a e to the minus kappa L over 2 is equal to minus d sine k L over 2, the minus sign coming from the fact that I'm evaluating the sign at minus L over 2. And then for the first derivative, I get kappa a e to the minus kappa L over 2. The derivative of a sine is equal to a cosine, so that's going to be a plus kd cosine kl over 2, because when I set x equals minus L over 2, the cosine remains positive. Okay, we're going to do the same thing. We're going to take the ratio, and when we take the ratio, what we find is kappa is equal to minus k cotangent kl over 2. So I'm going to now summarize the work that we've gotten. We've found two transcendental equations. For the even solutions, I have tangent KL over 2 equals kappa over k, and I have minus cotangent KL over 2 equals kappa over k. So we're going to define a parameter phi, which equals KL over 2. That's going to make our equations a little bit simpler. And I'm going to define a phi 0 as square root of 2mv0. That's a small typo. It's over h bar squared, square root of h bar squared, L over 2. And then kappa over k is equal to the square root of phi 0 squared over phi squared minus 1. All right. So these now are my transcendental equation. Tangent phi equals square root of phi 0 squared over phi squared minus 1. And minus cotangent phi equals square root of phi 0 squared over phi squared minus 1. Now, I know that you guys don't have a lot of experience with solving transcendental equations. And the way that we solve this is a method that's called the graphical method. Essentially, what we do is we plot the left-hand side of the first equation, and we plot the right-hand side of the first equation. The points where the lines cross are going to give us the solutions. And we do the same thing for the second equation. But you see the right-hand side of both equations is exactly the same. So I can actually put both transcendental equations on the same plot, and that's what I'm doing here. The red curves correspond to the even solutions. Those are the tangents. The blue are the even. Those are the tangents. And the red are the odds. Those are the minus cotangents. And then the black term is this term, square root of phi 0 squared over phi squared minus 1. In this case, when phi 0 is equal to 10, I believe. So phi 0 is a fairly large number in this expression. And you can see I have 1, 2, 3, 4 crossings of the blue curve. So there are 4 even eigenfunctions, and I have 1, 2, 3 odd eigenfunctions. The total number of bound states for this potential is 7. Notice further that the tangent goes from 0 to infinity as phi goes from 0 to pi over 2, whereas the square root of phi 0 squared over phi squared minus 1, that's infinity at phi equals 0, and it goes to 0 when phi is equal to phi 0. So I always will have a crossing of that blue curve, and I will always have at least one solution of this problem. So there's always at least one solution, and that solution is the ground state, and it's always an even function. All right, that was good. Let's now understand what we do with these solutions. So the transcendental equation is going to determine the ratio of A over C. If I go back and plug into that transcendental equation with a given root, a phi star, I will call it, which satisfies it's a particular value of phi that satisfies that transcendental equation, then I can get the ratio of A over C, and I can get the ratio of A over D. I also will get the energy. The overall scale of the wave function is determined by normalizing the final wave function. You don't get that by solving this transcendental equation. And as I'd mentioned before, the energy is determined by the solution value phi star, because phi star is equal to the square root of 2m v0 plus e over h bar times L over 2. So I can just use that to determine what the energy E is. All right, so we've solved this now with the Schrodinger equation approach. Now we're going to go back and we're going to solve it again with the factorization method. We've already solved a number of square well problems, or, well, they were infinite square wells or particle in a circle. So we have a good understanding of how we're going to solve this problem. In region 1, our lowering operator, and I put a superscript in parenthesis 1 to indicate this is what I have in region 1, that's given by 1 over square root of 2m p hat plus I h bar kappa, and the energy is minus h bar squared kappa squared over 2m. You should go through the exercise of verifying that that's exactly what you get. You simply need to calculate A dagger A, the raising operator product with the lowering operator, and you'll be able to verify those results. Now in region 2, because the potential is minus V0 and my energy is above minus V0, we have to use this tangent construction. So it's 1 over square root of 2m p hat minus I h bar k tangent k x hat. And the energy will come out to be h bar squared k squared over 2m minus 2V0. And then in region 3, oh, that's for the even solution. For the odd solution, it's the cotangent solution. So that ends up being p hat plus IH bar k cotangent k x hat. And the energy is E, again, is h bar squared k squared over 2m minus v0. And then in region 3, what we find is that the lowering operator is 1 over square root of 2m p hat minus IH bar kappa. The sign changed versus region 1. And again, this is what you get when you look at the subsidiary condition and make sure that your wave function goes to 0 as x goes to plus infinity. Or if you like, this is simply using the fact that if I pick a kappa bigger than 0, then my superpotential must be positive as x goes to infinity. Okay, similarly, the A of 1 was chosen by the condition that the superpotential be negative as x goes to minus infinity. So for the even solutions, we're going to use that first ladder operator in the middle region. For the odd, we're going to use the second. And we need to ensure that the wave function is even or odd when it is constructed from the subsidiary condition. I'm not going to go through that with you in this lecture, but it is something that you should be able to handle fairly easily. Now, the superpotential has to be continuous. That's one of our 10 rules about the factorization method. If you go ahead and you look at the continuity at x equals minus L over 2 for the even solutions, we'll find that that corresponds to kappa equals k tangent KL over 2 for the even solutions, and kappa equals minus k cotangent KL over 2 for the odd solutions. It just comes out immediately. We don't have to work. We don't have to take ratios or anything like that. We immediately get the two transcendental equations that we need to solve. And you can see these are the exact same transcendental equations as we had before. So they'll have the same solutions, as of course they must. Now, the wave function, as I mentioned, does require a bit more work, but you actually know how to do that. And I'm going to leave that as an exercise on your own to do if you'd like to. What I'm plotting for you here now are the energies of the system. These are the energies that you would calculate as a function of the depth of the potential V0, but recorded in terms of phi 0, which is 2m V0 A over h bar. A, I believe, is L. And in terms of those units, you can now see what these energies are. You can see that we get one solution only until this phi 0 is equal to pi over 2, and then we get two solutions. And we're looking at the negative of the bound state energy. So that energy is starting right at 0, and then it grows as I get bigger and bigger. You can see it depends linearly, approximately linearly, on this phi 0 when the phi 0 is large, and so forth. So all of the solutions for all of the phi 0s are actually incorporated and encompassed in this one plot. So this plot has a lot of information in it. So I just want to emphasize again, there's always at least one bound state. More bound states will occur as V0 increases. They always start entering right from the top of the well and then moving downward. And eventually, when the well gets very deep, I should have these energies approaching the energies of the infinite square well. And we know what those energies are. And so by looking at the difference from the bottom of the potential, you can predict what these energies will be in the large V0 limit. And again, you also can see, because these energies are going blue, red, blue, red, blue, red, that the states are going to alternate even, odd, even, odd, even, odd, etc. Okay, now for the wave functions, with the Schrodinger equation approach, you get the wave functions at the same time that you get the energy eigenvalues. Of course, you still have to normalize them, and that's often a painful exercise, even for a simple problem like this, like a particle in a finite square well. In the factorization approach, we actually determine the wave functions from the subsidiary condition afterwards. We have to match the wave function at the boundaries in order to make it work. But we actually also, usually we only have to do one normalization, but if you notice, we did not construct a factorization chain here. We instead solved this problem with a bunch of different single factorizations. And when we do it with a single factorization, we will have to find the normalization constant for each. But the subsidiary condition is a first-order differential equation. And we know for all of these first-order linear differential equations, we always can solve them and get the wave function. So we almost don't even have to think to get the wave function in the factorization method approach. So they're going to, of course, give you both the same functions. Both of the wave functions will need to be normalized at the end. That is something that is obviously true. Okay, with that, we have now reached the end of lecture 3 of module 8.